Welcome to Chem Vid. Today we're talking about thermochemistry. Thermochemistry is just another way of saying the chemistry of heat, or thermo. Alright, so thermochemistry, let's get started. Enthalpy is the word that we use to describe how much heat is contained in a system. So for instance, when you're talking about a chemical and how much heat it can produce when it breaks apart, that's what we call enthalpy. And the symbol for enthalpy is delta H. Don't ask me why it is not E. I don't know, but it's H. Endo versus exo. So endothermic means entering, like the EN in front of it. Energy is being absorbed into the reaction. And because it's entering the reaction, it has a positive enthalpy. And it feels cold. Well, or we should say less hot, because there is no such thing as cold. Exothermic is exiting. Heat is exiting the system, or is being released, and it feels hot. Therefore, it has a negative delta H. Enthalpy is what we call a state function. State functions means that you can calculate it in many different ways. We're going to calculate enthalpy in about 4 different ways in this class. But the path that we take should be independent of the answer. We should always get the same answer every single time. So enthalpy can be calculated in many different ways. We call that a state function. So let's talk about energy diagrams. Energy diagrams are ways that we diagram how energy is absorbed or released in a reaction. So the first thing, energy diagram, just a diagram that shows how much energy is needed for a reaction to occur. Transition state. This is when the reactants have come together and have collided, but have not become products yet. So they're in the middle of reacting. Activation energy is the energy required for a reaction to occur. So if I need 10 joules in order for a reaction to occur, that would be my activation energy. Think of it kind of like when you're baking and you have to turn it up to 400 degrees in order to get it to cook. Okay? The symbol for activation energy is E with a little a next to it. Initial energy is the energy of the reactants before the reaction, whereas final energy is the energy of the products after the reaction. And delta H, or the enthalpy, the heat content of the system, can be calculated by taking the final energy minus the initial energy, because that's how much energy was in the system. That was the heat content, or how much energy it started with. Effect of a catalyst, we know this. Speeds up a reaction. You learn this in biology. Enzymes are biology's catalyst. In chemistry, we have a lot more catalysts to work with. But the most important thing that I want you to make sure you highlight, underline, is that a catalyst works by lowering the activation energy. So a catalyst will actually require, instead of 400 degrees to cook your meal, it requires only 300, so you can cook it faster. That's why the reactions go faster. Okay? So when we're drawing energy diagrams, the first thing we want to look at is our axes. Okay? So we're trying to find out how much energy is being released in a system. So that's going to go over here on my y-axis, because I'm trying to look at how the energy is changing. On the bottom, I can put time or reaction progress, because what I'm looking at is I'm looking at the reaction, or the energy released or absorbed over the time of the reaction. So there are my axes. I'm going to start off with an exothermic reaction. So I'm going to give it a title so I know which one it is. There's no I. Mic. There we go. So when I start drawing this, the first thing I want to think of is, will the initial energy be higher or lower than the final? For an exothermic reaction, I know that the final energy, I'm going to be releasing energy, so I know that my initial energy has to start up higher than my final energy. So E final, E initial. Then, in a chemical reaction, what happens is you start off with your reactants. You increase in energy until you peak, and then you come back down and finish your reaction. In this reaction, I'm going to use the example of A plus B goes to C. A plus B are my reactants. That's what I start with. And when I finish, I'm at C. So right up here, right at this very top point, this is what we call the transition state. Because A and B have collided and hit each other, but they have not become C yet. They haven't created anything new yet. They just hit. So this is what we call the transition state. And I know that the activation energy is the energy it takes in order for this to occur, for them to react. So the activation energy is the energy from the initial energy to what it takes to react. Activation energy. Also on an energy diagram, I want to see what the enthalpy is. So when I look at the enthalpy is delta H equals E final minus E initial. So here's E final, here's E initial. So if I need to draw delta H, I'm going to draw it right here. Now, looking at this, since E final is a lower energy and initial is a higher energy, when I have a low minus a high, that means that I have a negative sign. That's why when we do exothermic reactions, delta H is negative, because final minus initial is negative. This is an exothermic energy diagram. Now before I show you what an endothermic energy diagram looks like, I want you to try it. Place the initial energy and the final energy and see if you can draw what would be considered an endothermic energy diagram. So if I look at an endothermic diagram, the initial energy is actually lower than the final energy. My reaction has to absorb energy in order to get to the transition state. Therefore, the activation energy is quite large. And if I look, final minus initial, in this case, would be a positive value. So I'm going to have a positive delta H. The transition state stays the same. It's at the hump. But if you notice, exothermic reactions take a lot less energy than endothermic reactions. Therefore, most of our reactions are exothermic. So what really is enthalpy? Enthalpy is just the energy that has been given off or absorbed in a reaction. And it's measured in kilojoules per mole. Now that's very important because that's the equation to find enthalpy, is kilojoules per mole, heat per mole. So let's first start off with one way to calculate enthalpy. With enthalpy, we have this equation. If I take the enthalpy, or the energy it takes to form my products, and subtract the energy it takes to form my reactants, that gives me the overall energy of the system. We need to define a couple of things first. If if a bond breaks, energy is needed in order to break the bond. When a bond forms, energy is released because the atom or the compound becomes more stable. This is important. Usually people think of it backwards. But when bonds break, you need energy to break those bonds. And then when bonds form, they release extra energy because they are more stable. Okay? Bonds break, absorbed. Bonds form, released. So when it says delta H with that little f, it means that it's how much energy it takes to form one of these compounds. So if I look at this, I can find out exactly how much energy will be either released or absorbed in a reaction by using the summation equation. So first things first, please write out this lovely little hint. all diatomic molecules and atoms in their standard state have a delta HF of 0. So anything that is in its natural state or its diatomic will always have a delta HF of 0. Write that down, star it, know it. Alright, the first thing I want to do in this problem is to find the delta HF of my reactants and my products. So I look over here, CH4, methane gas. I look over here, methane gas is right here, so I'm going to have a negative 74.6 kilojoules per mole of energy. That's how much energy it takes to form methane. Chlorine, I look over here, and chlorine is not there. But what's special about chlorine? Oh yeah, it's diatomic. And if it's diatomic, that means it is 0. But I have 2 chlorines, so I am going to have to multiply that 0 by 2. Well, we all know that's 0. But it's very important to remember to include your molar ratio whenever you do this. Over here I have carbon tetrachloride, and it's in liquid form, so that's this one. That's negative 128.2. And then again I have hydrogen, which is diatomic, which is 0. But there are 2 of them, so I also want to make sure I multiply that by 2. But again, that's just 0. So overall I have negative 128.2, and I have negative 74.6 kilojoules per mole. In my equation, I am going to add up, that's what this little guy means. This means sum. So I'm going to add up all of my delta HFs of my products. And that comes to negative 128.2 kilojoules per mole. And then I will subtract the sum of all of my reactants. So I look over here. The sum is a negative 74.6. Negative 74.6 kilojoules per mole. When I have a minus a negative, that turns into a big old plus sign. So when I solve it, negative 53.6 kilojoules per mole. So what this means is, when this reaction occurs, overall, it's going to release, because there's a negative, it's going to release 53.6 kilojoules for every mole of methane I burn. Okay? That's what that means. Our next way of using delta H is by using it as a conversion factor. So in this question it says, how much heat is required to vaporize 166 grams of water? So I'm going to use this information in order to calculate how much heat is released. Okay, so if I look at this, I know that I want to know how much heat, which is joules, is required to vaporize 166 grams of water. And I know in here how many kilojoules per mole it is required to either vaporize or freeze something. So I'm going to start off with what I know. I know that there is 166 grams of water being vaporized. In order to use this conversion factor, I need to be in moles, because that's the unit that they have. So I'm going to go from grams to moles. Then, once I'm in moles, I can go to kilojoules, because they give me that factor right here. So I look at the periodic table, 18 grams is 1 mole. And I look at my table, and it says in order to vaporize 1 mole, I need 40.7 kilojoules of energy. So for 1 mole, I need 40.7 kilojoules of energy, and that gives me 375.34444 kilojoules of energy in order to vaporize 166 grams of water. 375 with sig figs. So for homework, I want you to do the 3 problems, try them, see if you can get them. and we'll do the exit ticket in class.